Question 4. A 0.1 mole decimeter cubed solution of sodium hydroxide was gradually added to 25 centimeters cubed of a solution of a weak acid HX. Now, interestingly, normally I'm given a concentration and a volume, the volume of sodium hydroxide that I've added from my titration, but I've not been given the volume of sodium hydroxide from my titration, so I'm never going to be able to work out moles of sodium hydroxide added. But I have got a graph, so maybe I'm going to use the graph to work out the volume of sodium hydroxide that's added. So rather than having a titration volume, I've got this here, because I'm gradually adding it, so I'm not doing a titration as such. Graph was plotted, first reading after 20 centimeter cubed here of sodium hydroxide has been added. I've added another line here, this is the later part of the question, which we'll have a look at in a minute. I've got the acid dissociation constant, the equilibrium constant for the acid. Suggest a pH range of a suitable indicator for this titration. So that's anywhere where at the end point, the equivalence point or the end point, where the pH rises very quickly. So that's in between pH 7, because it's still starting to rise. Then it starts rising very quickly here, and then tails off at around about here, starts to tail off. So between 7 and 10, there's a rapid rise in pH. That's your equivalence point or your end point. Give the expression for the acid dissociation constant HX. So HX is going to make H plus, all acids do, and then remaining will be X minus. So HX goes to make H plus and X minus. So it's the concentration of H plus multiplied by X minus, the products, divided by the concentration of HX. Calculate the concentration of HX in the original solution. So this is where I've got a bit of a problem. So I could work out the concentration of HX if I could work out how much sodium hydroxide I've added to neutralize it. Well, I can use the graph here, because at this point here, at the equivalence point or the end point, where it rises very quickly, that's where all of the equal numbers of moles of sodium hydroxide have just neutralized equal number of moles of weak acid. So at that point, the sodium hydroxide and the acid have neutralized each other. They have just reacted in equal molar quantities, an equal number of moles. So I can read down from the graph here at this equivalence point, and it turns out to be 24. So 24 centimeter cubed of sodium hydroxide is needed at this equivalence point where the pH is starting to rise very rapidly. That's the volume of sodium hydroxide that I need to neutralize this acid. So now I've got the volume of sodium hydroxide that I've needed to neutralize the acid, and I've got the concentration. I can now work out number of moles. So 24 centimeter cubed sodium hydroxide, centimeter cubed into decimeter cubed, so going to a larger unit and divide by 1000, 0.024 decimeter cubed of sodium hydroxide, and needed to react with the acid. So I can do concentration. I know the concentration from the question. Concentration equals 0.1, that's from the question, equal moles divided by the volume. Therefore, number of moles equals these two numbers multiplied together, 0.0024. At that point, the number of moles of sodium hydroxide equal the number of moles of acid. So the number of moles of acid also equals 0.0024. I've got the volume of the acid, 25 centimeter cubed or 0.025 decimeter cubed. So concentration is moles divided by volume. Moles of HX equals the number of moles of sodium hydroxide at that equivalence point. So moles is 0.0024 divided by its volume in decimeter cubed, 0.025. I have got 0.096 mole per decimeter cube concentration of HX. Calculate the pH of the solution before any addition of any of the sodium hydroxide. So how do I do that? Well, I use the equilibrium constant. So I've got the equilibrium constant here, and I've got HX. I need the concentration of acid, which I've got. And now, because it doesn't mention a buffer, there's no mention of a buffer, these two concentrations are the same. So when I make a H plus ion, I make an X minus ion. So the HX dissociates to make H plus and X minus. So if it's splitting or dissociating, splitting in half, every time I make a H plus, I must make an X minus. So the concentration of H plus equals the concentration of X minus. So I can simplify it to H plus squared. I know the concentration of HX. That's that. I've just worked it out, 0.096. And I know my equilibrium constant. I can work out H plus squared. H plus squared equals these two numbers together. Square root it, 0.00159. pH equals minus log of it, 2.8. I'm going to do it to two significant figures because the value of my equilibrium constant is to three significant figures because the value of my equilibrium constant is to three significant figures. 2.80. So I've added a 0 here so that it's to three significant figures. You can't use H plus squared if you're using a buffer, but there's no mention of buffer, so I'm fine. Calculate the pH of the solution when half of the acid has reacted. So when you've added half of the amount of acid that you need to react, half of the acid, then the pH at half neutralization point, so when you've got half the acid reacted or half of the base reacted, at half neutralization, when you've got half the number of moles of acid and half the number of moles of base that I need to react, pH equals pKa. pKa is minus log to the base 10 of Ka, and Ka is 0.000262. I've got that from my original question here. So minus log of that is 4.58, again to three significant figures because the Ka is to three significant figures. So that's my pH, so that's just something to remember. pH equals pKa, or pH equals minus log to the base 10 of Ka at half equivalence point when you've added half and half. Put both points on the line, so on the graph. 4.58 is my pH at half equivalence point. So when half of the sodium hydroxide needed is added, 24 centimetre cubed to react, half is 12 and it was 4.58, so I've put that point on there. And I've also got the pH is 2.8 when before any of the sodium hydroxide was added. In other words, before any of the sodium hydroxide is added is here, volume of sodium hydroxide added 0, and I've got 2.5 there, or 2.8 rather.